The next section in chapter 2 that we're going to cover is 2.2, and that is polynomials. So in this video, we're just going to cover kind of what they generally are, and also we'll focus more on end behavior. In later videos, we'll get into the more nitty-gritty of finding zeros and really the main chunk of what we'll be doing with polynomials. Now, polynomials are something you've all seen before. You've dealt with these a lot. For example, here's a polynomial. Here's a polynomial, just 5. We have polynomials of higher degree, which we'll find out more about. So these are all polynomials. Like I was saying, you've worked with these a lot. You've probably seen the word polynomial before. And so we're just going to do a little bit more with those in this section. Now, to start off with, I just want to mention that we'll be using something called standard form. And so just so we're all kind of aware of this so we know what we're talking about, if a polynomial is in standard form, that means its highest power of x comes first with whatever its coefficient might be. We'll call that a sub n for now. And then the next highest power of x, so whatever n is, but we'll just subtract 1 from it. So for example, this first one might be 6, and then n minus 1 would be 5, etc., etc. So if n was 6, then n minus 1 would be 5. And so we would keep doing that until we end up with our last couple of terms, a1x, and then a sub 0 would just be our constant term. Okay, a couple of key points in this. These a's, so a n minus 1, etc., these are called coefficients. There's another definition. The very first term, so this one here, this is called the leading term. It's going to come into play a little bit later on in this video. The very first coefficient, the coefficient with the largest power of x, is called the leading coefficient. Whatever n is, so the largest power of x, this is called the degree of the polynomial. So these are all going to be words that I use repeatedly throughout this video, and throughout this whole chapter really we'll be coming back to polynomials. And then the last term that sometimes does come up is we sometimes look at this last a sub 0. This is called, you'll hear it called the constant or the constant term sometimes. Constant term. And this really kind of takes care of all of the definitions we'll need. So we'll keep referring back to these words throughout this video. Okay, now just as a really quick example, let's just take a look at, let's say p of x equals 7 x to the 8th minus 3 x to the 4th plus 2x to the 3rd plus 9x minus 1. All right, so in this case, we would say the degree is 8 because that is the largest power I see. The leading term, in this case, would be 7x to the power of 8. The leading coefficient is 7. The constant term is -1, and the coefficients, so let's just keep going with this, are as follows, 9. Now, part of the reason I wanted to do this example is you'll notice there's no x squared. So we can think of it as if there was a plus 0x squared. Just like when you write the number 102, you put 102 in there. It's the same idea here. It's called a placeholder. And then A3 would be 2. A4 is negative 3. Make sure you include that negative. A5, A6, and A7 are all the same. They're all 0. And then A8 is 7. Now, a lot of times I get the question, well, what about A9 then? Why do we have to stop at 8? And it's this for the same reason that, here, I'll kind of do this as an aside over here. It's the same reason that if I wrote, first of all, I could write 102. There's that placeholder. But you wouldn't write 0, 0, 102. That doesn't really make sense. You would just say 102. So there's kind of the aside. Polynomials work a lot like numbers in this way. Okay, so let's continue our discussion here. The next thing I want to talk about is graphs. So two key points to be made about graphs. This won't really come up in our class, but it does show up in calculus when you're thinking about a derivative, which you'll learn about later on in calculus. But one of the important things about polynomials is that they are continuous graphs, meaning there's no breaks, there's no jumps, there's no asymptotes, and they are also smooth, so no corners. For example, the absolute value, this is not a polynomial because that corner right there is not smooth. Because this not smooth. But once again, these two concepts here, continuous and smooth, you really won't have to worry about those too much until you're in calculus. Now the next particular thing about graphs we're going to discuss, and this will sort of take up the rest of our video, we're going to spend some time on this. We'll be discussing end behavior. And end behavior is a chance really to just think about the graphs of polynomials, but it also gives us a chance to practice some notation that you're going to see throughout this class and throughout your next levels of math, in particular calculus. All right, now in order to talk about end behavior, I'm first going to look at a couple of examples of some polynomials. So let's take a look at y equals x squared. If you graph this in Desmos on a graphing calculator, or if you just do it by hand, or you might just remember, y equals x squared is a parabola, so it looks like this. If I graph y equals x to the fourth on the same set of axes, it's very similar, except it sort of gets narrower, and then it also kind of gets wider there. This looks pretty terrible, but I think you get the idea. And then if I also were to graph, let's do one more, y equals x to the sixth. Same thing, it does basically the same thing, and then it goes like that. And so if I were to continue doing this, let's just say I had any y equals x to the power of an even number. Sorry for the typo. Even number. It's going to essentially do this. So I don't really care what happens in the middle. So sort of in this region yet. We will come back to that. That's where the zeros will come into play. What I'm really interested in are these end behaviors here. So if we were just writing this kind of colloquially, we could say the end behavior of all of these graphs it's the exact same. The end behavior is that they rise going to the right, they also rise if we're going to the left. So if you imagine yourself walking, starting at say 0, 0, if you started walking right and you went on forever and ever and ever and ever, you would end up rising. And if you went to the left, same thing, you would eventually start rising, and you would just continue rising forever and ever and ever. So we're going to come back to this, but for now, just know that if you have any x to the power of an even, this is the end behavior. Now let's do the same thing for an odd number. So if you take a look at any odd function and you start graphing them. So I won't do each example separately. I'll just say y equals x to the power of an odd. They essentially do this. They sort of squiggle through there, except for x to the power of 1 is just a line, but it still has the same end behavior. So in this case, we would say the end behavior is rise to the right, but it's actually falling if you go to the left. And so every single odd function would have this behavior. Okay. So now what we're going to do is relate this back to just any polynomial we could ever care about. And really what we're going to, before we get into that, we kind of have to think about what's happening as we go to the right and as we go to the left. So we're going to introduce some notation here, and then we'll go back to just every single polynomial possible. So if I'm going to the right on my axis, so that means, let's say I have a little person here and they are walking to the right. We could say in this case that x is actually going towards positive infinity, right? So if you go here, you could keep going, and x is going to get bigger and bigger and bigger. And so we would say, well, x is actually going to positive infinity. For example, x goes to 1,000,000, then 1,000,000,000, then 1,000,000,000, et cetera, et cetera, et cetera. It gets really, really big. So whenever we're going to the right, we say as x goes to positive infinity. Now, if we go to the left, it's very similar, except now we're getting to very large negative numbers. So we would say as x goes to negative infinity. And so this is the notation we're going to start using. Let's go back to our original examples. If I were to say rise right, well, this really means as x gets to really, really large numbers on the right, y is going to keep rising as well. So y is also going to get to really, really large numbers. If I say fall left, this means as x goes to a negative number that's very large, y is going to keep falling, so that means that y is also going to go to a negative number. Just to kind of complete this, if I said falls right, now we're going to say x is going to very large numbers. That's the right part. And then the falling part tells me that y is going down to negative infinity. So a graph that did this might look something like, let's say it went like this, maybe. Notice how as I move to the right, going to positive infinity, my y values are approaching negative infinity. So there's a visual representation. And then the last one, the last combination would be if I rise left, this means as x approaches negative infinity, y is going to keep rising, and so we're going to go to positive infinity. So these are the only possible end behaviors for a parabola. Sorry, not a parabola. Well, it is true for a parabola, but for any polynomial. And let's just kind of conclude here with a quick example, and then in the next video we'll do a little bit more nuts and bolts of end behavior. So let's just say you're given a graph not really too concerned with this one. Let's say it looked something like this. So here's some graph of a polynomial y equals p of x, and you have to find its end behavior. So you'd say, okay, it looks to me like it falls left. That's right here, right? So as we go left, we're falling. And it also falls when I go to the right. So notationally, the way you would write this is you would say, as x goes to negative infinity, as it goes left, the graph falls. As x goes to the right, as x goes to positive infinity, the graph also falls on that side. So you can think of this as really a language. You're converting between the English on the left-hand side here, this stuff is the English, and you're converting it to the math on the right, the mathematical notation. So that concludes our first video, just kind of generalizing polynomials, talking about their graphs, and the next one we'll focus some more time on the end behavior.